In this video, we're going to put everything together and talk about energy alongside momentum, but also get into the units that are used for energy and the fundamental components, and ultimately calculate power, introducing that physical property. So, one of the things that you may have noticed is sometimes physics almost sorts of rhymes. That energy and momentum, in this particular case, have a lot of similarities in the types of problems that we are doing and the types of strategies that we use to solve those problems. For energy, we have three main forms of energy and different calculations for that. Momentum, we only had one form. There's not a kinetic and potential momentum. There's one form of momentum. And then another somewhat difference of each of these is energy, at least the way that we've been looking at it, we are referring to it as a scalar. So the way that we are talking about energy here is energy is always considered to be positive. We're not worrying about a positive or negative direction for energy. There are some forms of energy that we can talk about in that form. But for now, for this mechanical energy, we're referring to that always as being positive. And momentum, of course, was a vector quantity. In this case, direction mattered. So if you had a positive or a negative momentum, you had to factor in that positive or negative. Whereas for energy, like it doesn't matter which direction it's moving, kinetic energy was always going to give you a positive. So those are some of the differences. We have different types of energy, and energy is a scalar versus one type of momentum, vector was important. Here are some of the similarities. Well, in a closed system, energy is always conserved. We say that the total energy before equals the total energy after. That might sound familiar from when we did momentum. We said that in a closed system, momentum was conserved. The total momentum before equaled the total momentum after. And in that case, we were dealing with these hit and stick, hit and bounce, or explosion type problems where you are looking at the momentum of multiple objects. Whereas for energy, we're typically just following the energy of one single thing. And then the other similarity is how that property is changed. When energy changes, we said that there was work being done. So we compared the initial to the final energy, and the change was the work. Work, force times displacement, changes your energy. When we saw this in momentum, we said that when momentum changes, it was an impulse that caused that change. So the initial momentum to final momentum was changed by an impulse. Notice that these are very similar quantities. Impulse is force times time. Work is force times displacement. So if you know the amount of time that the force is being applied, you might want to use momentum. If you know the distance that the force is being applied over, you might want to use energy. So since we have now multiple tools in our toolbox, we can actually solve some problems in many different ways. Here is a problem. What average force is needed to slow a car of mass 1,200 kilograms from 30 meters per second to 10 meters per second over a distance of 50 meters if the time is 2.5 seconds? Let's solve this three different ways and see that it can give us the same answer every single time. We'll start with SUVAT and F equals ma. If I am giving this many different variables to represent motion, SUVAT is often an option that we can use to calculate with some constant acceleration. We know that the initial velocity is 30 meters per second, the final is 10. The distance is 50 meters, and the time is 2.5. We're actually given 4 of the 5, which means to solve for A, I can use any equation that I want. I'll just use whichever seems the simplest. I like this one. V is equal to U plus AT. Plugging in my 10, 30, and 2.5, I get that A is negative 8 meters per second squared. It's negative in this case because we are slowing down, and it's moving in the acceleration is in the opposite direction of the velocity, causing that slowdown. So if I know an acceleration, I want to find the average force. Acceleration can be related to force using F equals ma. I know the mass and I know the acceleration. I will find that the force is negative 9,600 newtons. All right, put a pin in that. We'll come back to it. Work and energy. I know that my initial energy, in this case, is based on my speed. So it's going to be an initial kinetic energy. I'm given no information about a height. That plus the work, the change in my energy, is going to give me a final energy, 1 half mv squared. You'll notice here for work, I put in F times S, the force times displacement. If there was an angle, I would also include a cosine of theta, but there is no angle, so that drops away because the angle is just 0 and cosine of 0 is 1. Now, if I take this equation and I put it together with what I know, my initial velocity was 30, my final velocity was 10, and my distance that I traveled was 50, I can find the initial velocity. That's 540,000 joules. My final energy was 60,000 joules. So the work essentially is just the change in my energy. It goes down by 40 or 4,000 or 480,000 joules, which means the work, force times 50, is going to be equal to that change. And I'll find that the force is equal to negative 9,600 newtons. All right, one more example. We've got initial momentum, and momentum is always mass times velocity. That changes based on impulse. Impulse is force times the time to give us my final momentum. So the initial momentum plus the impulse is equal to my final. I plug in my numbers, which means I have an initial momentum of 36,000. A final momentum of 12,000. It is smaller because it's slowed down. And my change in momentum then is equal to the impulse. F times the time, which is 2.5, is equal to a change in momentum of 24,000, which gives me a force of negative 9,600 newtons. So each of these ways of solving this problem is equally valid. Sometimes you'll be asked for a specific thing. You'll be asked for, like, what's the work or what's the impulse, which will force you into one of these strategies. So you should be familiar with all three of these approaches. Okay, elastic and inelastic are a way that we can describe different types of collisions. And we didn't refer to this when we were talking about it in terms of momentum because elastic and inelastic are actually more of an energy consideration. For an elastic collision, we say that the kinetic energy is conserved. So that means that the energy before totaled up is equal to the energy after. Um, but specifically for kinetic energy, that means that no energy is being lost to sound or light or heat. Inelastic collisions, kinetic energy is not conserved. Almost every collision in the real world is somewhat inelastic, which means some of that kinetic energy, when you catch a bowling ball, there's some interactions that are actually going to cause some thermal energy to be formed. And that is going to decrease the amount of kinetic energy that comes out in the final because some of the energy is now thermal energy. In both of these cases, momentum is always conserved. So we can use momentum as kind of our centering point that we know that that's conserved, and then the kinetic energy is just something that comes out of that final velocity given by momentum. So let's figure this out by looking at an example. A toy rail car with a mass of 2 kilograms is traveling at 6 meters per second, collides with another rail car with a mass of 3 kilograms, traveling at 4 meters per second in the same direction. If the collision after the collision, the two trucks become joined together, what's the resulting velocity? Well, I know before I have a total momentum of the momentum, mass times velocity of each of them combined. And after, it's a larger car, essentially, of 2 kilograms plus 3 kilograms, a 5 kilogram object moving at some velocity. And 12 plus 12 is equal to 5v. So v, the final velocity of this thing, is 4.8 meters per second. Now, I can do the same setup with kinetic energy, and it is tempting sometimes to try to make conservation of energy work in this particular case. But with this collision and with any collision, you can't necessarily assume that kinetic energy is conserved. Momentum is always conserved. Kinetic energy often isn't. So let's compare that. Before, 1 half mv squared plus 1 half mv squared, I get 36 joules plus 24 joules, or 60 joules initial. After, 1 half times the total mass, which is 2 plus 3 times 4.8 squared. That's the 4.8 I just calculated. I get 57.6 joules, which means my total kinetic energy is actually smaller than it was because some of that energy was converted into heat. So in this case, I know how much became thermal energy. We might use that later on when we get into our thermal energy unit. But this inelastic collision is true because I've lost some of my kinetic energy. That did not stay the same. All right, next, let's just touch on some of the units that are involved in this world of energy. As a reminder, there are 7 fundamental SI units. In this IB physics course, we use the top 6. Now, we used this analogy earlier of primary and secondary colors. Like primary colors are red, blue, and yellow, but secondary colors are if we combine two primary colors, we can get something like orange. The way that we do this for units is we have derived and fundamental units. Fundamental are like our primary colors. We have seven of them. Derived units are these other units that aren't part of that seven. They are created by combining these fundamental units in different ways. So force is measured in newtons. We can express this in fundamental units. Um, the way that we do this is basically find an equation that solves for the thing that you're looking at. So force, newtons, and a common equation that we've used is mass times acceleration. Technically, you can use any equation um, that solves for force, but some of them kind of get stuck along the way. So let's use this one. That means that newtons is kilograms, my unit of mass, times my unit of acceleration is meters per second squared. Or we can write it like this, kgm s to the minus 2. This is the equivalent in fundamental units for newtons. Newtons under the hood have kilograms times meters per second squared. The same idea is can be true for joules. We can figure out for joules the fundamental SI units of this. Now we have a lot of different equations for joules. I want to show you what this would look like for each of the equations. Gravitational potential energy is mass times gravity times height, which is kilograms times meters per second squared times meters. We can simplify that. We'll do that later. Kinetic energy is 1/2 times mass times velocity squared. 1/2 doesn't have a unit, so we'll just leave that empty. Mass is kilograms, velocity is meters per second, but that's squared, so the square is going to factor into each of those. Elastic potential energy is 1/2 times k times the chain delta x squared. 1/2 again is unitless. K is newtons per meter, and the stretch is meters, and that's going to be squared. Now, this has newtons. Newtons is derived, so we can expand that to what we saw before. That's kilograms times meters per second squared. So that's a much longer string. And then work is also measured in joules. That's a force times a displacement. Force is newtons, displacement is meters, but again, newtons is kilograms times meters per second squared. Now, for each of these can combine. Kilograms times meters per second squared times meters. Those meters can be combined to be meters squared. Here, this squared goes into meters and into seconds. Turns out each of these are going to simplify to the exact same thing. And you can spend the time and look at each one. But joules in fundamental units is kilograms times meters squared per second squared, or meters squared seconds to the minus 2. This is a good one to know, and it's really good to know where it comes from. And any of these equations will get you to that same list of fundamentals. Now, units matter on graphs too. We've seen this before. If you pull a giant spring back 10 meters and graph the force, you might get something like this. And we've talked before about slope versus area for a simple graph. Slope is always your y-axis divided by your x-axis. So my units are newtons per meter, or newtons meters to the minus 1. We know that as being our spring constant. That's K. So in our elastic potential energy, we've seen that. Now, the area is always going to be your y times the x for our units. So that's newtons times meters. But we saw in our work that newtons times meters is effectively the same thing as joules. The meaning of that then is work, or the energy that is being added, which means that work, oftentimes we talk about it as a force times displacement. But if the force is not constant, we have to use a strategy like this to figure out what the work is going to be, find the area under the curve. All right, and the equations that we've seen for work can ultimately give us our definitions for these different types of energy. So work and energy are very closely connected. If you have a dog climbing up a ladder, and we know what the force of the gravity is, basically, if the dog's climbing up the ladder, it's going to be exerting a force that's equal to gravity, mass times gravity. We know that the work is just the force times how far that force is being applied for. Well, this force we know is gravity, and the distance is going to be basically your height. So how high the dog climbs. If I plug those in, mg is my force, h is my height. Well, it just gives me mgh. That is the same as potential energy. So the work that the dog is doing is converting into potential energy. So work gives you potential energy. Same idea here for a dog pushing a stroller from rest. If you push something, it's going to speed up. Here, work is still going to be force times the displacement. So let's look to see what do we know? We know that the force that's being exerted is mass times the acceleration. We know that in this displacement, comparing some of these things, the final velocity, initial velocity, acceleration, and displacement, we're going to assume that it starts from rest in this case. And if that happens, I can rearrange this to solve for the displacement. So the final velocity that you have squared divided by 2 times the acceleration. I can plug these in for my force and my displacement, respectively. And you'll see that acceleration shows up on the top and the bottom. And what I'm left with is just mass times velocity squared over 2, or 1/2 mv squared, which shows that if you are starting from rest, the work that you do can be converted into a kinetic energy, 1/2 mv squared. And there are some scenarios where we are not adding or removing energy from the system. So this waiter carrying a heavy tray of food, constant velocity across the room, the force is up, the displacement is over once they are moving, so not accelerating at all anymore. We say that the force is not in the same direction as displacement, so no work is being done. Another way to think of it is it doesn't change the tray's energy. If the energy tray is moving at one velocity and is staying the same the whole time, the kinetic energy is not changing, which means there's no work being done. Here we have the moon orbiting the Earth. Is the Earth's gravity doing any work on the moon? Well, no. The moon is experiencing a force inward towards the Earth, but the displacement is this way. The moon is orbiting. Another way to think of it is the moon isn't gaining any energy. It's not changing its potential energy, and it's not getting faster. It's moving at a constant speed the entire time. So the kinetic energy stays the same as well. That is circular motion. While there's a force, there's no work being done. Same thing is true if you have a question like this. A particle of mass m is moving with a constant speed v in a uniform circular motion. What is the total work done by the centripetal force during one revolution? Again, this question is just trying to trick you into thinking that you can calculate it, but it's just zero again. The circular motion, that force of centripetal force, the net force towards the center, does not do any work because it is not in the same direction as the displacement. All right, one last concept that is kind of related to this idea of work. Um, Two physics students, Maria and Paige, are going from the first floor to the second floor on their way to the next class. Maria walks up the 3-meter staircase, takes 15 seconds. Paige runs up the staircase in only 5 seconds. They both have a mass of 60 kilograms. Which student does the most work? Well, they feel very different. And if you've ever run upstairs or walked upstairs, you know that it's a different experience. But we know that work it's just a distance and a force. If they have the same weight or the same mass, the weight down, Fg, is going to require the same amount of force up to push them up the stairs. And the same stairs, so same force, same stairs, same weight. There is something that's different though. Work only depends on force and distance. What we experience as a difference is something else. It's power. Power is the rate at which work is done. So how much work is done in a given amount of time. In that case, we know that Paige did the same amount of work in less time. So Paige had more power in that particular scenario. You can calculate power using these properties of work and time. Power P is just work W divided by T, which is the time. Time is seconds, work is joules. Power has a new unit, it's joules per second, otherwise known as watts. Watts is something that you have seen before. You've maybe seen watts in terms of electricity, and we'll talk about watts again when we get into our electricity unit. But different appliances have a different wattage. That watts is a power. We can find these equations. This power is equal to work divided by time in the IB Physics data booklet. There's also another equation that if the velocity is constant, the power is force times velocity. So let's see all of this in one final example problem. Biker travels at a constant speed by applying a force of 500 newtons over 20 meters. If they cover this distance in 5 seconds, calculate the following: a velocity, a work, and a power. So here's our biker going 20 meters. in that 5 seconds. If I want to find velocity, velocity is simply just a distance divided by a time. 20 meters, 5 seconds. The velocity that the biker is doing is 4 meters per second. Work is a force times the displacement. 50 newtons times 20 meters is a work of 1,000 joules. And then power, there's actually a couple different ways we can find this. We had an equation, power was work divided by time. We calculated work was 1,000 joules. Um, and power is also force times velocity. So if the work is 1,000 joules and the time was 5 seconds, we can calculate a power that way. If the force is 50 newtons and the velocity that we calculated was 4 meters per second, we can calculate it that way. Now, turns out that both of these are technically actually doing the same thing. This velocity, we calculated by a displacement divided by time. Force times displacement would be work divided by time gives you power. So both of these scenarios will give you the same thing, that is 200 watts. All right, so some takeaways. You should be able to describe the difference between elastic and non-elastic collisions, and then calculate the amount of energy that's retained in a non-elastic collision. Also, the amount of energy that's lost. You should be able to derive what a joule is in terms of fundamental SI units, and then use the area under the curve to calculate the work in a variable force. Um, Work of a variable force like a spring, and then finally be able to calculate power if you know work and time or you know a velocity and a force.